Hello, my name is Kavya, and in today's video we're going to be talking about isomorphic graphs. But before we dive into that topic, I do want to cover a few larger ideas related to graphs in general, the first being graph theory. So, graph theory is the area of mathematics that contains topics like isomorphic graphs, and as the name suggests, it does focus on graphs. So, the graphs in graph theory represent networks, right? Networks are just connected things, and the things in question depend on the data that is being modeled, but in graphical form, this is the connection of vertices via edges. And if you don't know what those terms mean yet, no worries, we will go over that right after this. But all you need to know for now is that vertices are being connected using edges. And graph theory also has a lot of applications in computer science because graphs are very valuable tools for modeling algorithms, data, so they prove very useful for solving problems that require visual representation. Alright, now we're going to talk about the formal definition of a graph and clarify some of those terms like vertices and edges. So the formal definition reads, a graph G equals VE is an ordered pair of a vertex set V and an edge set E. So a vertex set is just the set of all the vertices in the graph, and an edge set similarly is a set of all the edges in the graph. So our example here is the graph C4, and you don't have to worry about the specific names for graphs. We're not really going to be talking about that in this video, but since this is our example, I will explain the name. So C, let me just change the color here. Alright, C represents cycle, or stands for cycle. So this is a cyclical graph because if you go around and trace the edges, you'll see that if you go around this loop, you can go around an infinite number of times, right? It's a cycle, forms a cycle. So that is why this is used, or C is used to denote this graph. And we also have the number 4. And I've already written it represents the number of vertices, but this is a good segue into what vertices are, right? Vertices are these red dots here. So you have 1, 2, 3, 4. 4 vertices in total, which is where that number 4 comes from. And these are the connection points between two different edges, right? And edges are these lines here, like connecting vertex 1 to vertex 2. They connect two different vertices. Alright, so the vertex set for this graph is 1, 2, 3, 4, right? All the different vertices contained in the graph. And the edge set is all the different edges, right? So we have 1, 2, 2, 4, 4, 3, and 3, 1. So if you go around this cycle in that order, you should be able to get all those edges. Alright, so that was our first example. Hopefully that cleared up what some of those terms mean. And now we're going to look at one of the common misconceptions that people might have about the number of vertices in graphs. So in this star graph right here, we can see that we have 5 red dots and 5 edges, right? Each edge is a different color. So like I said earlier, vertices are the connecting points between two different edges. But looking at this graph, it's not as simplistic as our earlier example. So you might be a little confused and might say, okay, well, if it's the connecting point, then why isn't this a vertex, right? You might go around and say, well, then these should all be vertices, all the points that I'm marking in black here. Well, if we were to say that all of these are vertices, then that would raise a problem, because just earlier we said that there are 5 edges on this graph. But if we make all these new vertices, suddenly each edge has been subdivided into 3 parts, right? We have this yellow edge here, 1, 2, 3. There are now 3 lines. And similarly, we have all the other edges. They're also, oh, that's a bad line. They're all divided into 3 parts, as seen. So if we have 5 edges and we divide each into 3 parts, then there are 15 total edges now. But we just said that there were 5 edges. We can't have, that can't be like true at the same time, right? There are 5 edges and 15 edges for the same graph. And the problem here is that we're altering the basic structure of the graph by changing the number of vertices and the number of edges, right? We go from 5 to 10 vertices and 5 to 15 edges. And this is important in isomorphism because we're trying to see whether two graphs are the same, and that relies on their structure. So if we change the basic structure of a graph, then that could change our answer to the question whether two graphs are isomorphic or not. So that's just something to keep in mind going forward, that vertices will just be your ends, like the ends of each edge. When they connect, that's where your vertex point lands. Alright, and then our final point before we move on to isomorphism itself is just the difference between one type of graph and the other. So when I first mentioned graph, if you haven't heard of graph theory before, you might have thought I was talking about the coordinate plane. But the difference between the graphs we're talking about and the coordinate plane graphs are that coordinate plane graphs are a visual representation of an equation, right? So this example here, you can see the equation y equals x plus 2 visually represented on the coordinate plane here. But our graphs are representations of some data or any scenario, but they're represented by connecting vertices using edges, right? So they're two very different things, so it's important to make that distinction between those two types of graphs, but that's just something also to note going forward. Alright, so now we're going to start talking about isomorphism. So firstly, why is isomorphism important? Well, the main thing is that it helps us identify whether two graphs have the same structure and therefore are the same, even if they are presented in different ways, right? Because two different people may draw two different graphs or two graphs differently, and that may lead us to think just by looking at them that they're completely different graphs. But when we analyze the structure using some of the tools we'll see in our isomorphism definition, like mapping, we'll see that really they are the same graphs. And it could also go the other way, right? Just because two graphs look similar doesn't mean that they are the same graph. Alright, so now we have the formal definition of isomorphism. And this reads, let G equal VE and H equal V prime E prime, then the function that maps G to H is an isomorphism of graphs if the resulting maps, the function that maps V to V prime and the function with tilde that maps E to E prime, are both bijective. So just to expand on some of the terminology used here, G equals VE is something we just saw. So it's that some graph G equals the vertex set V and the edge set E. Similarly, we have some graph H with a vertex set V prime and an edge set E prime, right? And prime is this little symbol here. It's just used to show that there are two different vertex sets and edge sets. Alright, and then we have the function that maps G to H, right? This here, and is an isomorphism of graphs if the resulting maps. So the function that maps V to V prime, and that's just saying that you're mapping the vertices from graph G onto the vertices in graph H, and then the function with tilde that maps E to E prime, so you're mapping the edges in graph G onto the edges in graph H, and tilde is this symbol here, which is just used to show that even though these functions both have similar notations, right, f colon, they're still different functions, right, they have different purposes. Alright, and then the final term that's probably the most important in this definition, apart from isomorphism itself, is bijective. So what does bijective mean? It's a combination of injective and surjective. So injective means one-to-one, right? If you have a set of inputs and a set of outputs, then every input must pair with a unique output, right? That means it's one-to-one. So that's injective. And then you have surjective, is onto, which just means that everything must have a partner, right? You have that same set of inputs and outputs, there can't be one input and one output without a partner, right? Everything has to have a partner. So in summary, it's like saying that everything has to have a unique partner. And then a visual representation of this would be if you have your set of inputs, A, B, C, and your set of outputs, 1, 2, 3, you can see that A goes to 1, B to 2, and C to 3, so everything does have a unique partner. And if you map it differently, right, you say A goes to 2, C goes to 1, and then B goes to 3, it still satisfies that condition. So it doesn't really matter if you draw the connecting lines a little differently, but what really does matter is that everything is connected with a unique partner. Alright, so first we're going to talk about a non-example of isomorphism, because this will just help me go over some key ideas that will probably help you make more sense of an actual example of isomorphism. So to begin with, I have color-coded the vertices in each of these graphs, right? We have the graphs G and H, and just to note, G and H are not the names of every graph. It's just the terms like I've used here, but you can use any letters or numbers to name your graphs. Alright, so in graph G, we have the vertex A is red, and in graph H, the vertex 1 is red. So that means that A corresponds to 1. Similarly, B is orange, 2 is orange, so B corresponds to 2, C to 3, and D to 4. And that is shown if you look at vertices here, right? I have the function that maps G to H for vertices. So what does that mean? It means that if I plug, say, the vertex A into this function that maps the vertices from G onto the vertices from H, then I should get an output of 1, right? Because A is being mapped onto 1 in graph H. Similarly, if I plug in B, I should get 2, C should give me 3, and D should give me 4. Okay, so now we've seen that the vertices from G can map onto the vertices from H. So that satisfies the first property of our isomorphism definition. But we also have to make sure that we have a valid mapping of edges. And in order to do that, we're going to use what we know about our corresponding vertices, right? We've already seen that A corresponds to 1 and B goes to 2. So based on that, if we have some edge AB, then there should also be an edge between 1 and 2, because those are the corresponding vertices and should make up a corresponding edge. And we do have that here. So if we just keep going with BC and 2, 3, CD and 3, 4, and finally DA and 4, 1, then we'll see that we can go around and we have 4 corresponding edges. But something you would have noticed before, let me just get rid of the red here. Alright, is that in graph H, we also have this red edge going from vertex 2 to vertex 4. And I've also drawn that here, right? So we have a blank space there because we're looking for an edge that can correspond to that edge in graph H. So using our corresponding vertices, we can see that we have 2 and 4, orange and green, so that has to correspond to B and D in graph G. But there is no edge going directly from B to D in graph G. So that blank space we had waiting to find a corresponding edge would have to be marked with an X, right? There is no corresponding edge that we can find in graph G. And since this wouldn't be considered a valid mapping of edges because not every edge has a unique partner, we would say that this is not an isomorphism. So the key takeaway from this example is probably the number of vertices and the number of edges in each graph, right? We saw that every vertex corresponded to some other vertex because there were 4 vertices in each graph. But we had 4 edges in graph G and 5 edges in graph H, and as a result, we were left with our 5th edge not having a partner since there were not the same number or not an equal number of edges in each graph. So one thing to keep in mind is that if you don't see an equal number of vertices or an equal number of edges when you first look at two graphs, you automatically know they are not isomorphic. So with that being said, let's take a look at an actual example of isomorphism. Okay, so and I've already done the mappings, but let's just work through it together and see how you can get those mappings. So the first thing you want to do is you want to just make some observations about your graphs, right? The first thing I see is that I have a triangle here, and I also have a triangle here. Similarly, I have another triangle on this side, and I have another triangle on this side in G2. And another similarity I see is that there's an edge, oh, that's a bad edge, my bad, but there's an edge connecting the topmost points of both triangles in G1. There's also another edge like that in G2. And there may be other similarities you see, and if you do, that's good. But this is just my way of saying that if you do find similar shapes, that will make your mapping a lot easier, right? Because I can already see that maybe F could correspond to 3, maybe C could correspond to 4, and that narrows down the amount of trial and error I have to do for each of my graphs when I'm doing my mappings. Alright, so let's get rid of those lines, and using what we've seen, let's maybe try to map. But before we do map, using what we saw in our non-example, we should check to see if these graphs have the same number of vertices and edges. So if I look at G1, I have, alright, let me just circle 1, 2, 3, 4, 5, 6 vertices, and in G2 they're already numbered, so I can see I also have 6 vertices here. That's good. But now I want to make sure I have the same number of edges. So let's count. I have 1, 2, this is one whole edge, so 3, another whole edge, 4, this is another whole edge, 5, another whole edge, 6, another 7, and my last 2, 8 and 9. Alright, so those, let me just, there. Alright, so those are, I have 9 edges in G1, those are my edges, and now if I go through and count the edges in G2, I have, oh, that's a bad line, my bad. Okay, I have 1, okay, again, just ignore that line, but I have 4, right, from this like square shape on the outside. I have 2 more from this triangle shape, 2 more from this triangle shape here, and then a final connecting line. So I can see that I also have, right, 4, and then the 2, and the 2, and the 1. So I have 9 edges in this graph as well. So now that we've seen that we have an equal number of vertices and edges, we can use that to start doing our mapping, or at least know that these graphs have a possibility of being isomorphic. Okay, let me just undo all the circles and lines. Okay, and based on the patterns we saw earlier, let's try to start mapping. So F is this topmost point on this triangle here, and 3 is the topmost point on this triangle here based on the association we made earlier, so we can say those two correspond. Next we have A, right? A, I can say that A either corresponds to 1 or 2 because they're both bottom points of this triangle, but let me just say it corresponds to 2. Okay, now let's do E. Since I already used up the other 2 points of this triangle, then I know that E would have to correspond to 1. Okay, now let's do this. Let's take a look at the other triangle. So I have B, that's one of my endpoints. So let's just say, or not, let's just say, sorry, B would have to be 5 because as we can see, this is where you have to be a little more careful, because in G1 you have yellow goes to green. So in G2 you also have to have a yellow vertex connected to a green vertex, right? If I did 6 was green, it wouldn't connect to 1, which is yellow, so that wouldn't be a possible connection. Okay, now let's do C, right, the topmost point. So this is also blue. And that leaves me with my last points, D and 6. Okay, so now I have what seems like a valid mapping of vertices, right? And if we go through and see, it is a valid mapping. Everything corresponds to a unique partner in the other graph. But now we also have to make sure that we have a valid mapping of edges. So based on our corresponding vertices, let's go through and try to draw corresponding edges. So our first edge, AF, we have red and orange, so let's do that here, right? AF corresponds to 2, 3, using the corresponding vertices. So if we keep going, FE corresponds to 3, 1, and AE corresponds to 2, 1. Now this big edge here, EB, corresponds to 1, 5. Let me redraw that edge. Let me redraw it again. Okay, 1, 5. BD, green to purple, corresponds to 5, 6. BC, green to blue, corresponds to 5, 4. And the finishing line of this triangle, CD, corresponds to 4, 6. Then we have this big edge here, AD. AD corresponds to 2, 6. And our last edge is this one here, FC, which corresponds to 3, 4. Okay, and now we see that we also have a valid mapping of edges. So based on that, we know that these two graphs are isomorphic. Alright, so now one final thing I want to talk about is how this relates to competition math. So this could relate to combinatorics, right? There aren't necessarily going to be problems that specifically ask about isomorphic graphs. There could be, as I talk about in the later points, but largely it might use skills that relate to combinatorics, right? Counting, because in this you're categorizing, in isomorphic problems, you are categorizing two graphs based on their structures, right? You're counting vertices and edges to see if they have the same underlying structure and are therefore the same graph. So that could be where you see something like that in that larger area of math. Next, are they isomorphic? You could get a question like that, possibly. So you'd be given two different graphs, and they might ask you, are they isomorphic? And if so, you just use the skills we've seen here, and you try and answer that by first counting to see whether they even have the same number of vertices and edges, and then going from there to try to create valid mappings. And finally, you may get a question like how many different graphs are possible, right? You might have a scenario where you're asked to model it using a graph, and you'd have to see how many different graphs you could use to model that same scenario. But to determine whether those graphs are really different, you'd have to use your knowledge of isomorphism to see whether those are the same graphs structurally, or if they're actually different, both how they're in the ways they're like drawn and based on their structure. And yeah, that wraps up today's lecture video. So thank you for watching. I hope you found this interesting and that you learned something new.